Let's do one last one. 216. Okay, now as the numbers get larger, it depends on your number sense. Should we factor them all the way down, or should we factor by these perfect squares only? So you have to kind of get comfortable with the way that makes the most sense to you. People that have good number sense and know the perfect squares, that might be a faster way. People that their number sense isn't quite as strong, then just break it down little by little. And this one is going to take a long time to break down, so I'm going to break it down and show you real quick. So 216, 2 times 108, but 108 breaks down into 2 times 54. 54 breaks down into 2 times 27. And so notice I just started breaking it down with 2's, and then when I got 27, I said, oh, well, what about 3's? 3 times 9 is 27, and 9 is 3 times 3. So 216 is 2 times 2 times 2, times 3 times 3 times 3. I have a lot of multiplying in this breakdown here. So we're going to use that to simplify this giant square root. Square root of 216 equals square root of 2 times 2 times 2 times 3 times 3 times 3. There we go. Now, every time I have a pair, there's a nice square root there. Hey, here's another pair. That's another nice square root. So, the square root of 2 times 2 is 4. That square root of 4 is the whole number 2. That has a nice answer. 3 times 3 is 9. Square root of 9 is 3. That has a nice answer. Now, all of these answers are multiplying each other. But the square root of 3 times 3 is 9, gives me this whole number 3. Now, the square root of 2 is left over, and the square root of 3 is left over. These are under the square root. These two guys are stuck. They are not coming out with a nice answer. Okay, so we broke down the square root, but we can simplify a little bit more because we have a whole number 2, whole number 3, that equals 6. And under the square root, we have a 2 times 3, so that's square root of 6. That is our simplified square root for this giant square root number. Now, what would that look like if we did the shorter way? So we would take 216. I'm going to go back to green. I wanted to do all of these in green. So I'll go back to that. Okay, so we're not going to worry about 2, we're not going to worry about 3, we're not going to worry about 7 or 5. We're only going to try to divide this number by only perfect square numbers. Only these numbers in the list. And again, we're after the biggest number. I'm getting some scratch paper and a calculator so I can go a little faster. Let me get that off the screen. Okay, so we're going to take 216 and find out, does 4 go into 216? Clear. 216 divided by 4. It does. 4 times 54. But don't stop. That may not be the best one. We want to try to find the biggest one in this list. So let's try, after 4, let's try 9. 216 divided by 9. Oops, I didn't type it right. 216 divided by 9 by 9. Ah, it worked. 9 is better. It's bigger. But I don't want to stop at just the next one. I want to find if there's a bigger one. And because I have 2 different square numbers, there is a bigger one for sure. So let's keep trying. Let's try 16. 216 divided by 16. Now that came out with a decimal, so it's not working. Let's try not 16 but 25. I'm trying to put that in the screen so you can see. 216 divided by 25. Okay, that has a decimal. That didn't go in evenly, didn't work. We tried 25. Let's go to 36. 216 divided by 36. Ah, that works. So we have 36 times 6. this one, notice the 9 times 4 makes the biggest and the best one. This one's best. I found the biggest perfect square number that goes into 216. Now, if you're not sure, you could go a little higher, but just for the sake of time, we're going to quit because we know that's the best one. So 36 times 6, that is the square root. Now, the reason I like this is because 36 is nice. The square root of 36 has a nice answer. It equals 6. Square root of 36 is the whole number 6. There's no square root on that. Square root of 36 equals the whole number 6. But this part is not nice. It's stuck. The 6 is stuck under the square root. It doesn't have a nice answer. So I have to multiply by that extra piece that's left over. 6 times the square root of 6. So this is the simplified answer. So we learned it 2 ways. You could practice both ways, or kind of decide one and get really good at this one or really good at that one. But let's quit there on this one. And now I want you to flip the page to the back. Okay, so I also want you to be able to do square roots on the calculator. Now, sometimes in algebra, a lot of times in algebra, the calculator is not going to help because it's not the best answer. These are the best answers, the simplified square roots to do algebra with. Because when you get a decimal, you start running into round off errors and problems with the decimal being how many decimal digits. But there are other times when we do need the calculator. So, how would you do this calculator? Now, there are problems that I hope you're going to memorize. 144 happens to be a perfect square, and I don't want you to use the calculator for that. I want you to know that answer. But there's other square roots that you may not know. But if we just, for the sake of practice, let's do the square root. Now, look at the second power button. And above the second power button is a square root symbol. So if you want the square root button above the second power, you can activate it by hitting the second command and then the second power button, which activates the command above the square root. So let's do that to do square root of 144. So I'm going to hit the second button, then I'm going to do the second power button, and you see the square root symbol comes up, 144, close the parenthesis, and we get 12. Now that's one that I hope you never need to use the calculator to get that answer. I want you to memorize that one. But there's others that you may not have memorized. Let's see, 625. I think that has a nice answer. But you may not know what it is. So we go to, it's clear, second square root, 625, close the parenthesis, and it does have a nice answer. It's 25. 25 times 25 is 625. Let's see. Let's do the square root of 1.69. And so we type in second square root. You should try this by yourself. Pause the calculator and see if you can get the right answer in your calculator. I'm sorry, pause the video. Do the calculator problem, see what you get, and then compare it. So pause, try it on your own. Okay, I hope you paused and did it. And now let's check. What should you get? 1.69, close the parenthesis, and we get 1.3. Okay, these are all examples of square roots that had nice answers. And they're nice because they're whole numbers or easy decimal numbers. But square roots have another side to them. Like the square root of 18. We tried to do that problem before and we said, oh, that's not a nice square root. And we simplified it. And we simplified it and got this one here. I'm reaching to my notes. and we got square root of 18 was 3 root 2. It didn't come out completely nice. We couldn't get the square roots all gone. What does that look like in a decimal? That's clear. If we take the square root of 18, close a parenthesis, and we get this crazy decimal, 4.242640687. Now it turns out these square roots that are not nice, they have decimals, and the decimals are infinite. They never stop, and the decimals never repeat. What's going on with the calculator? Well, the calculator ran out of memory. It could only do 1, 2, 3, 4, 5, 6, 7, 8, 9 decimals, and then it got full of memory. It couldn't do any more work, and it had to quit. But that's not the real answer. That's only an approximate round-off answer. Anytime you use a calculator for square root, the best you got is a round-off. Now, it's a pretty good round-off, but it's not perfect. So, then we have to choose how we're going to approximate this. Well, let's say we're rounding to 3 digits. So the third digit is number 2, and after the third digit is a 6. The 6 means we're going to round the 2 up. So it's 4.243. That's an approximation. Even this is an approximation. These are not exact answers anymore. Okay, here's another example. Square root of 2. Second square root, put in a 2, close a parenthesis, and it too has one of these crazy decimals. It goes forever. The calculator just ran out of memory. And if we round this off to 4 places, 1, 2, 3, 4, the 2 is in the 4th place. 1 after it means we're going to round down. So it's 4142. So it's approximately 1.4142. Okay, these are round-offs. They're not exact, they're not pure. But that's how you do it in the calculator. Now, here's one more example I want to do here. The square root of negative 49. Hey, wait, now, 49 is one of those perfects. 49 is 7 times 7. Let's do the square root. Clear. Square root button. Oops, wrong one. Square root, I keep pushing the wrong button, it's down further. Second square root. And I'm going to type in the negative 49. Now be careful, this little button down here at the bottom is the negative. Don't confuse it with subtraction. So subtraction will give you a syntax error. But it's a negative 49, so I'm going to hit the negative button and then type in the 49 and close a parenthesis. And what's your guess? Negative 7? 7? Let's try. What? Error. According to the calculator, this has an error. The answer does not exist. How come? Well, it's because square roots can only reverse second power. Now, is this possible? B squared equals negative 49. What number times itself equals negative 49? Is it negative 7 squared? Well, that's negative times, oops, I'm crowding. I can't crowd this thing over here. Negative 7 squared is negative 7 times negative 7. It equals positive 49, not negative 49. This isn't working. You cannot do anything to a second power and get a negative answer. This is a positive times a positive, or a negative times a negative is never negative 49. This is not possible. So it's impossible to do a second power to have negative 49, which means it's impossible to do the square root. Okay, so takeaway from this. Turns out square root of a negative inside is impossible. Does not exist. Anytime you have a negative under a square root, you can't do it. Okay, good. Let's stop there. on these square roots, we're going to transition now, talk about classifying numbers. Okay, this is a big subject change. We're looking at a new concept here. We're not looking at math. We're looking at something that's more like science. In biology, they classify the animals. You have fish, you have reptiles, you have mammals. In math, we classify our numbers, and we have different group names for the different numbers. And the first group name, that's the set of numbers that I want you to learn about, is the real numbers. Think about everything in this box is all the real numbers. Now, in the box of real numbers, they're going to break down into other groups, like our animal kingdom. You break down the animals into mammals and fish. So mammals have one pattern and fish have a different pattern. Real numbers break down into two big patterns. One pattern is the numbers that are called rational. I'm going to use this little pound sign or hashtag sign as an abbreviation for the word numbers, versus another group that is called irrational. Oops, I need to irrational. Sorry, my spelling can be really bad sometimes. Okay, now what's the difference between these two groups? These are fractions. Rational numbers are just fractions. Irrational numbers, ir just means not. So this group, they're not fractions. There's a bunch of numbers out there that we cannot make them into fractions, and a bunch of numbers out there that we can make into fractions. Now I want to concentrate on this rational group, because if we break down the real numbers, like all animals, into mammals, the mammals break down into other groups, like dogs. And the dogs break down into other groups, like hunting dogs and pets. And those break down into like poodles and chihuahuas. So we can keep breaking down this animal kingdom. But the rational numbers are fractions, like -7 over 3 or 8 over 5. But this group of rational numbers breaks down into a simpler fraction. And let's make a box inside the box called integers. Because integers are a special kind of fraction, like 6 over 1, or -7 over 1, or even 0 over 1. These are all integers because 6 over 1 is 6, -7 over 1 is 7, -7, 0 over 1 is 0. These are special kind of numbers that we call the positive, the negative, and 0 counting numbers. All right, now in that group, we can break that group down smaller into a smaller group. Now these last two smaller groups are not super important, but the categories do exist. These are the whole numbers. Now, what are the whole numbers? They are zeros and the positives. So that would be like 0, 1, 2, 3, ... That's the whole numbers. Now, inside the whole numbers is a final group that we're going to call the natural numbers. Now, what are the natural numbers? The natural numbers are 1, 2, 3, ... So we count with the natural numbers. That's nature. Now, if we take the natural numbers and combine it with 0, it makes the whole numbers. If we take the natural numbers and combine it with 0 and combine it with the negatives, it makes all the integers. Now, if we take all the integers and combine it with all the other kind of crazy fractions, we get all the rational numbers. And then lastly, there's this other group, the irrational numbers. The irrational numbers are a little bit more unusual. They're numbers like pi, like the square root of 2. The negative square root of 17. When you go into algebra 2, there's a special number called e that's very similar to pi. Now, here's a note about these irrational numbers. They're decimals. Because I'm going to give you a number and I want you to tell me, is it rational or irrational? And if it's a decimal, here's how you know. The decimals never stop, never repeat. If it's a rational number, the decimal will always stop or repeat. So like 12, the decimal stopped at, there's no tenths or hundreds. 25, the decimal stopped. So you get 25. 1.3, the decimal stopped after 3/10. These are rational numbers, and we know because they're decimals are stopping. There's other numbers where the decimal repeats, like let's see, 1 divided by 27. It's a fraction. And if you look at that, you get 0.37, 0.37, 0.37. There's a rational number, and its decimal is repeating on us. If you get any decimal that repeats, you know it's